Okay, in this section we're going to be taking a look at polynomial functions and their graphs. Let's begin with the definition of a polynomial function. As you can see, it can have many terms, with the requirements being that each of the coefficients have to be a real number, and each of the powers or exponents have to be non-negative integers. So in other words, these powers cannot be fractions. We call this a polynomial function of degree n based on the term that has the highest power. That will determine what the degree is. So sometimes it could be a polynomial of degree 5 or degree 3, degree 2. The coefficient of the variable with the highest power is called the leading coefficient. Okay, below we have some examples to illustrate what a polynomial function is versus one that is not a polynomial function. The first two that you see here are examples of polynomial functions, and you want to get very good at being able to tell what the degree as well as the leading coefficient is, because that is going to govern the entire section and many of the types of problems that you're going to do throughout the remainder of the chapter. So in this first example, this classifies as a polynomial function based on the definition that I just showed you, because each of the coefficients are real. This is a real number. This is a decimal, but that's a real number. And this is a real number. And furthermore, the powers that you see are non-negative integers. So this classifies as a polynomial function. Here it may be take a little bit of thought in order to figure out what the leading degree is. Notice that in this one, the highest degree was 5, and therefore we call this a polynomial function of degree 5. It is classified based on what the highest degree is. Therefore, you need to be able to tell what the highest degree is. And as I was just stating here, you got to put a little bit of thought into this. You don't really need to multiply this whole thing out, because that would be a lot of work, but you do need to be able to tell what that one term is that has the highest degree. And that would come from multiplying this times this times this. That's how you can tell what the degree and the leading coefficient is. So that, remember that when you're multiplying like bases, you add up the powers. So the leading coefficient would be -3, because this times this times this would have a -3. And then as far as the power on the base, you add the powers. 4 plus 1 plus 1 is 6. So this would be your leading term. So this is a polynomial of degree 6 with a leading coefficient of -3. Over here you see examples of things that are not polynomials, because the difference between a polynomial and something that's not a polynomial is very evident in the graph. So these have completely different shaped graphs that do not have the same characteristics as a polynomial graph. So the reason that this is not a polynomial is because, remember, in the definition we said that the powers have to be non-negative integers. The power that's on here, if you recall from previous chapters and previous courses, the way you write anything that's underneath a radical in power form is you keep the power that's on this base over whatever the index is, and the index of a square root would be 2. So the square root of x is the same thing as x to the 1/2, and again, the definition of a polynomial function is that this power has to be an integer, which you can see it is not. So this term stopped it from being a polynomial. Likewise, g of x also has a problem. The problem with this one, again, if you recall things that you learned about how we write various terms in power form, when a term is down in the bottom, in the denominator, if you want to raise it to the top and write it in power form, any power that occurred in the denominator is actually a negative power if you're going to float it to the top right up next to that -3. So this is the same thing as -3 times x to a power of -2, again, because that power was in the denominator. Going back to the definition of polynomial functions, you cannot have any kind of powers that are negative. They need to be non-negative, and therefore this is not a polynomial. Okay, so just a few examples. Now, what you've concentrated on a lot of thus far are polynomial functions that were less than degree 3. In this section, we're going to concentrate on polynomials of degree 3 and higher, and you will be expected to graph them by hand. For certain things, we'll use the assistance of our calculator, but the mainstay of this section will be that you will be showing that you algebraically know how to get X and Y intercepts, as you did a lot of that in section 3.1, as well as end behavior, finding, and also finding other points on the graphs. So let's take a look at, just as a reminder, some of the things that you have concentrated on thus far, and then let's move forward. So this is a function that you have had quite a bit of, not only in this course, but in the previous course. This is called a constant function. This is the same thing as y is equal to 3, and then of course that's what this graph is. It is a picture of several points that all have a y value of 3. So this is called a constant function because every point on this line has a y value of 3. So we say that the y value is constantly 3. Moving on to the next picture, we have an example of a linear function. And you do quite a bit of this in MAC1105 as well. We don't concentrate on it as much in this class because we're trying to get you to concentrate on developing your skills for graphing higher degree polynomials. But this is a linear function, and that's the name we give to a function whose highest degree is first degree. And of course you remember, hopefully, that this is the y-intercept right there, and this is the slope. So from any point on this line, specifically the y-intercept, you can go up to over 1. Because remember, this is rise over run. That's where that graph comes from. And then all of section 3.1 was devoted to this. Okay, and the specific details used to get this kind of graph. So I'm not going to go into that because you've just come through a section where you've hopefully listened to that lecture video. So in section 3.1, we have polynomial functions of degree 2. The name for that is a quadratic function. So this is a quadratic function that opens upside down, as you saw in section 3.1. It has a vertical shift of 1. So instead of starting right here at 0, it's lifted up 1 unit and it opens upside down. So as I said, in this section, we're going to concentrate on polynomial functions of degree 3 or higher and go through all the skills needed to graph by hand. Okay, so let's see. Wanted to show you some pictures of what you can expect your graphs to look like whenever you are graphing something that is higher than degree 2, which is what this is going to concentrate on. Graph of a polynomial function is nice and smooth. No sharp edges and no discontinuity. Discontinuity is a name that we use when something has a broken part in the graph and it's disconnected. So there will not be any discontinuity, and it'll be a nice smooth graph, no sharp points, no sharp edges, just nice smooth rounded curves. Okay, the very first thing that you are going to use each and every single time you try to graph one of these on your own is you're going to use what's called the leading coefficient test. So you're going to have to memorize the 4 possibilities for the leading coefficient test. So we're going to go over that right now, and each time I do a problem with you, produce the graph myself, I'm going to refer to the leading coefficient test. There will be several steps that you're going to go through to try and create the graph. So let's start with this leading coefficient test. So what you're going to do each time you get a problem is you're going to identify what is the term with the highest degree, because the coefficient of the highest degree is the leading coefficient. So what this says is that, let's say your highest degree is odd. Let's say that the very highest power in the problem is x to the 5th degree. So your highest power, n stands for the power, is odd. And then you're going to look at the coefficient out front. If the coefficient in front of the odd power is positive, it's going to go up on the right and down on the left, and then you will be left to determine what happens in between the two ends. So what we are studying here is a way to talk about what is the right side and the left side doing, and that's called end behavior. And the leading coefficient test is what helps us determine what the ends are doing. So sometimes you will see when you get into My Math Lab that they will be prompting you into saying what happens on the right with respect to the word rise and fall. So when it's going up, we say that it's rising. So on the right side of the graph, this is rising, and on the left side, it's going down, which we refer to in mathematics as falling. Rising on the right, falling on the left. Again, that will happen if your highest power is odd and the leading coefficient in front of it is positive. Remember, this is how we say positive in mathematics, when a number is greater than 0. Okay, notice that when the degree is odd, that the ends go in opposite directions. If one goes up, the other one goes down, and that will be true of this case also. These are both the two cases where the highest power is odd. So if the highest power is odd, but yet the number in front of it is negative, that means that it's the reverse of this. So instead of up on the right and down on the left, it's going to go up on the left and down on the right. So we say that the left side and the right side of the graph, or the right end, is falling. So maybe, and then know that this one's the reverse. In contrast to that, if the highest power in the problem is even, let's say that the highest 4th degree, again, you're going to have to look at the coefficient, which is why this is called the leading coefficient test. You're first going to look for the highest power, then you're going to look at the number out front of it to see if it's negative or positive. So if that highest degree is even and the number out front is positive, both ends will go up. And that is the behavior of anything that's even. When the highest degree is even, both ends will either go up or both ends will go down. So if it's even and the leading coefficient is positive, they'll both go up. And if the highest degree is even and the leading coefficient is negative, then they'll both go down. And again, you're always going to be having to, it'll be the work that you're going to do to create the entire rest of the graph once you know what the ends are. You're just going to start the problems by analyzing the end behavior of the graph. Then you're going to determine what's going on in the middle. How many times does it turn? Where are the X-intercepts? Where are the Y-intercepts? Do these points bounce off the X-axis? Do they go through the X-axis? All of this is considered graph theory, and it is the reason that you are not allowed to create the graph solely by means of your calculator. You will be doing it all by hand because you're not at that point in your math career yet where you can say that you understand any of that. So we build understanding, and when you are a couple of classes beyond this, you'll be allowed to do more of just using your calculator to create something. Right now, you're showing that you know how to create them by hand. Okay, moving to the problems. First, let's just make sure that you understand the leading coefficient test and what that means with respect to the ends of the graph, the end behavior. Okay, so first of all, let's just answer these questions together. Is the degree of this polynomial odd or even? Remember, that is based on solely the term with the highest degree. That's all you're going to be looking at, which this one's simple because you don't need to multiply anything out to determine what the highest degree is. It's just staring you right there in the face. So is the degree odd or even? There is that highest degree. You can see that it's a 3, so the degree is odd. What is the leading coefficient? The number out in front of it. So the number out in front of it is a 1. Coefficient will be found out in front of the term with the highest degree. Determine the end behavior. Remember, the leading coefficient theorem is based on this, the odd or even nature of the polynomial, as well as the leading coefficient. You're going to use these two in unison. Okay, so does the right side of the graph go up or down? And you can just draw a picture as you're trying to think about this. You don't need to be worried about what's happening in the middle. But anytime you have odd degree, the two ends are going to go in opposite directions. One's going to go up, one's going to go down. Now specifically, how do you tell whether the right goes up and the left goes down or vice versa? By using this as well. Not just this, but using both of these. So when it's odd degree, the right and the leading coefficient is positive. This is a positive 1. You're going to have the right side going up and the left side going down. So what does the right side do? Here's the right side of the graph. It rises. What is the left side doing? Going down. So we say that is called falling. So it falls. Use your calculator to confirm your answer. You may have to manually adjust the window to see the entire graph. You are only to use your calculator to get the graph if the direction says to do so. But other than that, you'll be expected to show all the algebra that goes specifically into how do you get the middle of the graph, because there's no work in determining what happens to the ends. But you're going to be expected to answer these questions. So let's see if we really got this answer right. Does it truly rise on the right and fall on the left? And let's get used to, do we have to manually adjust the window? The window is something that we talked about in Chapter 1. Section 1.1 was dedicated to adjusting the window when you need to on your calculator. Let's continue to work with that. So, in calculator, and should have had one in Chapter 2, because this class is completely devoted to graph theory. So if you want to put this in, you're going to use this key right here that has the X, the T, the theta, and the N. All these other things that are on this key are devoted to other math classes that you may or may not take. And it's in function form right now. That's just a mode that this calculator can be in. I'll touch this mode key just so you can have a little experience with it. When you touch mode, it tells you what kind of graph you're going to be doing. We're doing something that is in function form, f of x form. When you get into pre-cal or trig, you'll be doing parametric and polar equations. And, that's what this mode is. It determines what kind of function you're doing. So we're doing y is equal to. So press this key with the x on it. And when you want to put a power on it, you raise it up to whatever power you're trying to put on it. Then it's plus 3. Tap the x again. And there's two different ways to put a square on an x. You can either touch this squared key. Let me float this up here a little bit. If you see right here in the first column, about 5 keys down, there is a little x squared. You can put it on like that if you'd like, or you can go use this caret key. Raise it up to a power 2, just like I raised it up to a power 3. It'll work for any power. Then it's minus x minus 3. Make sure you press enter after you have the entire function in, so your calculator absorbs the entire expression. And then let's just try and press graph. I mean, you can start with what's called a standard window, which is, you obtain that by pressing the zoom key. And then if you don't like the way the graph looks because it's cutting off various parts of it, then you can adjust it manually by touching the window key. But on the zoom key, you have pre-made standard template windows. So zoom, I'm going to use that standard window. Let's see what the graph looks like. Oh, there we go. So for this particular graph, it was good enough. You can see that it cuts through the x-axis here, here, and here. So these are what we call X-Intercepts. This is a local maximum. This is a local minimum. In other words, high point and low point right in that vicinity. This is also called the Y-intercept. Those are the things you're going to be concentrating on in addition to end behavior, but doing them by hand, showing the algebra that gets those rather than just copying a picture from your calculator, because that just means all you know how to do is press something into a calculator. But anyway, with respect to this problem, we had answered that it rises on the right and falls on the left, and this picture confirms that. Okay, moving on to the next problem. Maybe a slightly more challenging, but why I picked this problem. Maybe it's not as clear what the leading coefficient or the highest degree is. So all you have to do is multiply this by whatever the highest degree would be in this expression right here. You don't need to really FOIL this out, but if you did FOIL it out, the very first term you would get would be x to the second degree. So just consider that this factor right here is going to contribute an x squared to the product that I am now trying to consider. This is going to contribute an x to the first degree. So the leading term, highest degree with the leading coefficient in front of it, would be negative 4x cubed times x squared times x. So there would only be that one coefficient, negative 4 times 1 times 1, and the powers are 3 plus 2. Remember, when multiplying like bases, you add the powers, 3 plus 2 plus 1. So that would be x to the 6th degree. So for our purposes of graphing, wanting to use the leading coefficient test, we now know what the highest degree is, as well as the leading coefficient, and we can answer these questions. Is the degree of the polynomial odd or even? You can see it is 6th degree, therefore it is even. What does even mean? Well, you have to use the fact that it's even in addition to the leading coefficient, which is negative 4. It's just the number that's out in front of the term with the highest degree. Determine the end behavior. Well, what happens when it's even degree with a negative out front? First of all, when it's even degree, both sides go in the same direction, not one up and one down as we just had in this problem. So both go in the same direction, and if the coefficient out in front of that even degree is negative, they both go down. If the coefficient that was out here was positive, they would both go up. So what does the right side do? It falls, goes down. What does the left side do? It also falls. Use your calculator to confirm the answer. You may have to manually adjust the window. So in doing this problem, we're going to try and put this whole problem in here. And we can mess around with the window to try and see the whole thing. Now, the higher the degree goes on a problem, you can see that this is much higher than the degree that was in the previous example, which was only 3rd degree. The higher the number, the higher the graph is going to go, and the lower it's going to go. It's going to shoot up very high, and it's going to go down it's going to go down low as well. So you may have to use very large numbers in the window that you're going to manually adjust to see the entire graph. So let's try and work on that skill a little bit, where we try to get that graph, the entire graph, to appear. Okay, pressing it in the calculator. Let's go to y is equal to, clear out what's there, and begin pressing this in. So it will be negative 4x raised up to a power of 3. Then we have a parenthesis. Inside of it we have x minus 1. By the way, when you're pressing in a minus, it's this key, not this. Not that little negative that you see right there. That is only for leading coefficients. Like for instance, when I began pressing this polynomial function in, I did use this key right down here for the negative 4, but not for this. Okay, for this I just use the minus key. So close up that parentheses, put a power on it. That power is 2. I'm just going to use this little x squared key to put the power on it, this key right here. So there's the square. And then I also have another parenthesis with an x plus 5. Press enter to make it absorb the entire expression that you have just calculated. Now when you go to push graph, remember we chose a standard window. Can't see much of that. You may be able to see enough of it to answer the question, but sometimes you won't be able to see enough. In fact, oftentimes it can make you answer the problem wrong because you're not seeing the proper pieces of the graph. So it's a very important skill to obtain, or you know how to handle the window. Okay, so let's go to window here. I want to see what's going on up here. So I need more positive y values. That's called y max. All right, now because this is 6th degree, we need some pretty big y values, and you're going to see. I'm going to let those y values be 2,000 and see what happens. They shoot up very quickly. Keep that in mind when you're graphing these sort of things. Look, you still can't see it. You can't even see the top. So I'm going to try 4,000, 5,000, 6,000 just to see what's happening. I could always change it. Remember, you're doing y max, positive y values. Let's see what happens when I do this. Just messing around with the window. Almost, I can almost see the top of it. So I'm going to give myself even more here. Maybe 7,000. And I'm going to give myself a little bit more y min. Since I've gotten into such big numbers with the y max, I'm going to try negative 1,000 here. See what that graph looks like. Okay, pretty good. Now if you want to see a little bit more action down here, you can give yourself more negative y values, which are also called y min, if you want to just see more of it. Okay, but anyway, as we stated in our answer, you can clearly see that both the left side and the right side go down, and that is, you know, we had already answered to that effect. But we answered without cheating with the. This can sometimes be like a nice answer key. So it was even, it was negative, and we said that both the left and the right side fell, and in fact that graph verifies it right there. Okay, here's another example where specifically they're trying to see, are you going to get trapped by only being able to use a calculator? Because if that's all you can do and you don't understand the theory that you have just been taught called the leading coefficient theorem, then you're not going to know whether the graph is right or wrong. There's some students that they just, bam, put everything in the calculator and they accept whatever it says without really thinking, hey, what did I just learn? Do they really back each other up? What I've learned and what my calculator is saying? Or is there a problem? This is meant to be used as a backup, not as the only thing that you can do. So let's see what happens with this. Now here they are specifically telling you what to do with your window. Again, this was something that they went into in Chapter 1, Section 1.1, because you're going to be doing a lot of graphing, sometimes using your calculator. The first window is always with respect to the x's. They're telling you to manually set your window with -8 to 8 to 1. This is going to be the x max. This will be the x min. And what you're seeing right here is called the x scale. Likewise, this is the y max, y min, and y scale. Okay, so they're saying, here's a graph. Use this window. Is this a complete graph? So let's try it. Let's go and first of all, put the function in. Clear out the other one, and we're going to put in, remember when the first number is a negative, you have to put that in using this key down here, or it's not going to graph it. If you want to use a minus sign, then it's this one over here. So let's go ahead and press those terms in. So it's minus x raised up to the 4th power, and then it's plus 8x raised to the 3rd, plus 4x, put a square on there, last term is positive 2. Press enter to absorb the entire function. Then we're going to set the window as they've requested in this problem. We're going to do a negative 8 by 8 by 1 scale on our x's and a negative 10 by 10 and a scale of 1 on our y value. So press window. All right, my x min is supposed to be negative 8. My x max is supposed to be positive 8. And the scale for my x is supposed to be 1. Then come down here, I'm supposed to set the y min to negative 10, the y max to 10, and the scale to 1. Once you're done with that, so that you don't erase any of these selections, press second, quit. Okay, then let's see what the graph looks like. All right, so what this graph is telling me is that it goes up on the right and down on the left. Well, does that back up what I have learned regarding the leading coefficient theorem or the leading coefficient test? Do those two answers verify each other? This says up on the right, down on the left, but yet this is what I've learned. That if the highest degree is even and the leading coefficient is negative. Okay, even means that, first of all, that gives it away right there. When the highest degree is even, they should both go in the same direction. Specifically, this guy right here tells you they should both go down. On the left, it should be going down, and the right, it should be going down. So is this complete graph? Definitely not, because if it was a complete graph, you would be seeing the other side going down. So in order to try and get the, a complete graph, what you want to try and do is have the ability of messing around with the window. So let's try and adjust this window to see if maybe we can get a better graph for what's going on here. So let's go into window and maybe stretch that y min and that y max a little bit to see what happens, because we're not seeing enough of that. I'm going to try negative 500 on my y min, and for my y max, I'm going to go all the way up to 1,000. See what the graph looks like. Pretty good, but let's try and give ourselves a little bit more x max. Let's see what's going on over here. So maybe, let's see, I can maybe stretch it out to 20, see if I can see more of that graph. There we go, looking pretty nice. So I didn't need quite that much x max, but I can now definitely see that both sides go down, and that's exactly what it should be doing. This was a polynomial of even degree with a negative leading coefficient. Therefore, both of these, both the left side and the right side, should both be falling. And now we have a complete graph that verifies it, all because we're refining our skills of adjusting the window. Okay, let's take it all the way to producing a graph on our own. Okay, so here we go. We're going to go through some of the other steps, but take it further. We're not going to use the calculator unless we need to just do a little calculation. So here we go. For the given function, create a graph by hand, discuss the end behavior of the graph, show all algebraic calculations for the x and y-intercepts of the graph, as well as any other points that you may need to find. Just, is the degree of the polynomial odd or even? So you see that that highest power is odd, therefore the ends are going to go in different direction. One's going to go up, one's going to go down. Let's make that decision. What is the leading coefficient? Leading coefficient is 1, which is a positive number. One is a positive 1. So when you have odd degree, with a leading coefficient that's positive, the right is going to go up and the left is going to go down. We are about to now go further and determine, hey, what's happening in here? What kind of twisting and turning occurs in between these two ends? Because you're going to go from these ends and you're going to create a nice, smooth, continuous graph. Okay, does the right side of the graph rise or fall? This is my little picture. I'm rising on the right-hand side right here, and I'm falling on the left. Make sure to put that in my picture. We're going to gather all this information that we're laying out, and we're going to put it on the actual graph. Okay, find the X-intercepts, also called zeros. Points where the graph hits the X-axis are called zeros because the Y value is 0. In fact, that's how you find them. You let Y be equal to 0 and solve the remaining equation. We're also going to state the multiplicity of each 0, which I have put the definition for here. But first, let's do this part. Let's take the entire function, set it equal to 0. In other words, put a 0 in place of the f of x. So I'm going to start it right here just in case I need more room, but I can finish it down here. So I have x cubed plus 3x squared minus x minus 3. So you're going to need to get refreshed with all your factoring. There are several types of factoring, but when you have 4 terms like this, factor by grouping is a real strong indication of how you're going to get that all the way factored. So let's try it. If you remember factor by grouping, you take 2 terms at a time. Let's take the first 2. Take out the factor that's common to these 2 terms, which is x squared. Both of these terms contain at least an x squared. You always put 1 parenthesis when you're taking out a GCF, a common factor, and you ask yourself, that common factor times what will give me this back again? That would be x. This common factor times what would be 3x squared, positive 3. Then let's go to the back 2 terms and do the same thing. Take out the common factor. These have nothing in common other than the negative 1. So take out negative 1. You always put 1 parenthesis next to that common factor that you've just taken out, and then use it as a multiplier to regain both of these terms. Negative 1 times x is negative x. Negative 1 times positive 3 is that negative 3 that you're seeing. Then you do it one more time. When you're factoring by grouping, you're actually taking out a greatest common factor 3 times. We did it once here, and we're about to do it the 3rd time. Okay, so what this term, because this is considered the first term, those 2 factors, this is considered the second term. What they have in common is x plus 3. And then what goes in the second parenthesis is these GCS that you've taken out. So let's continue that right here. You can continue factoring because there's another type of factoring that can be applied here. You haven't factored it completely. You have done factor by grouping, but you can still break down this. This is called the difference of squares. And if you recall, it is sorry about that. It is broken down by taking the square root of this term and taking the square root of this term. So to finish this, you're going to have more parentheses to get that factored. Square root of x squared is x. That is what fills out the first position of each parenthesis. Square root of the second term is 1. That fills out the back position of each parenthesis, and then you alternate the signs. So we now have this completely factored, and once you bring each factor down to first degree, this is first degree, first degree, first degree, you can then find the zeros of the polynomial function, also referred to as the X-intercepts. So in other words, these are where the graph is going to hit the x-axis. Now you can, or it's up to you whether you go through this part, but through the zero factor property, you're setting each factor equal to 0, because if the product of these 3 is 0, that means either this is 0, or this is 0, or that's 0. Any of these could have been 0 for that to happen. That's called the zero factor property. It's what allows you to create these little equations and get your x-intercepts. Bringing the 3 over here would be -3. So that's going to be one of your x-intercepts. Bringing this 1 over here, you would have x equal to -1. And then bringing this over here, you would have x equal to +1. So our graph is going to hit the x-axis at -3, -1, and 1. Okay, we also have, remember these are also called zeros. That'll be important later on in this chapter. We also have what's called the multiplicity of each x-intercept, the multiplicity of each 0, because they could use either this word or this word. So in my math lab, when they start to ask you what is the multiplicity of each of these zeros that you just found, all you have to do is go back up to what they looked like in factor form and identify the power that was on each of these parentheses. Each of these had a power of 1, and what tells us what the multiplicity is. It's just a fancy word for the power belonging to each factor. So this 0 has a multiplicity, I don't have room to write that out, of 1. This had a multiplicity of 1. Each one of them had a multiplicity of 1. Because based on the multiplicity, you can tell how you're going to hit the graph at that particular 0. We're going to hit right at x equal to -3. But how do we hit it? Do we have the graph just bouncing right off of that point? In other words, just touching the x-axis at that point and bouncing off of it? I mean, you could even call it ricocheting right off of the x-axis. Or is the graph going to go right through that point? And I'll be able to demonstrate that a little better as I actually do the graph. But when the multiplicity is odd, that means you are going to go through the point. You're going to go through that x-intercept. I don't know where I'm getting my spelling from here, but okay, so we're going to go through, and that's because the multiplicity of every single one of these x-intercepts is odd. So not only do you want to find the x-intercepts, you want to recognize what is the multiplicity associated with that particular 0. Okay, y-intercept. Y-intercept, I mean, we did both of these things in section 3.1 when we were graphing parabolas by hand. We found the x-intercepts by letting y equal to 0, by allowing y to be equal to 0, and we found the y-intercept by letting x be 0. So now we're going to find that. Okay, so let's see. Our function was f of x, but we're plugging in a 0 for x is equal to, let's see, our equation was, our function was x cubed plus 3x squared. You see how it gets rid of all of these? Minus x minus 3. So this term's gone, this term's gone, this term's gone, and you have just the -3. Or in other words, f of anything is considered to y. So y is equal to 3. There's no such thing as the multiplicity there, just on your x-intercepts. So we have a lot of information here. We know what the ends are doing, and we also know what the x-intercepts are and how to approach those x-intercepts. We're going to approach them by actually making the graph go right through the x-axis at these points rather than bounce off the x-axis. We'll get to problems where that's going to happen. Turning points. You also need to have some background theory on that. The number of turning points, just in general, is you're going to look at the degree of the function. So if the highest degree is, whatever the highest degree is, you're just going to subtract 1 in order to find out the maximum number of turning points. So when it says, what is the maximum number of turning points for this graph? Well, this graph, this polynomial function was of degree 3. Remember, the degree of the polynomial is whatever the highest degree is. So this was degree 3, and if we take that degree and subtract 1, so this is what we refer to as n. And if we subtract 1 from that, we have 2. So at most, we're going to turn twice. We're going to have 2 turning points at most. Can sometimes have less than this number. That'll be the absolute maximum number of turning points. Let's put all of that together. Okay, I think what you should do first is go put your X-intercepts in, because where you're going to put the ends of the graph will be dictated by where these X-intercepts are. So our X-intercepts were at -3, 1, 2, 3, right there. And we also had an X-intercept at -1. And we also have an X-intercept at +1. Okay, so because our X-intercepts don't go any further than -3 and +1, I can now put my ends in. Remember, according to the end behavior that we talked about right here, the right is going to go up and the left is going to go down. Right is going to go up, left is going to go down. So come to this rightmost point and you can put an arrow above it somehow. Don't get on top of it. Just lift yourself up a little bit from that rightmost point. Remember, you're going up on the right. On the leftmost point, you're going to be going down. So get underneath it so that you could end up on these graphs. Now you're going to figure out how to come at these points. But we already talked about multiplicity and what multiplicity meant with respect to how you're going to approach these X-intercepts. We said that for every single one of these X-intercepts, we are going to go right through the X-axis. And that's because they each had an odd multiplicity. So we're going to go right through here. Now I'm not going to do any other points. Like, in other words, some students will say, how low do I go? We can figure that out if you want to do some extra work in here. But one thing that could help us is that we also did a Y-intercept. So the Y-intercept was -1, -2, -3. We calculated that. So if we want to know how low to go here, there it is right there. Remember, we're approaching these X-intercepts and going right through the X-axis. So we're going up. Again, how high should you go if you want to? Not if you want to, you should do this in order to get the most accurate graph possible. Hold on for 1 second. I want to write what we did first. We did the X-intercepts first. Then after we plotted the X-intercepts, then we placed our ends. Placed the ends properly based on the end behavior. Okay, then right now, I knew how low to go because of that X-intercept of -3, but now I'm kind of wondering how high should I go right here. So what you could do is a skill that you should have whenever you are graphing by hand, and that is, how do I plug in a value to figure out what the Y partner is? Kind of wondering what happens here. This is -1, this is -2, this is -3. In between any two X-intercepts, if you have, a value, you can just choose any value that's in between those two X-intercepts to figure out what the height is associated with that X value. So this would be -2. I'm kind of wondering, what is this graph doing at X equal to -2? So just because I want to know how high to go, I want to know what's going on at X equal to -2. And whenever you want to know the partner, any X value, you just plug it in. Now that you can get your calculator to help you with. You can also do it by hand if you want to, but if I'm going to plug in -2, it would be -2 cubed plus 3 times -2 squared minus the -2 that I'm plugging in minus 3. So all I did is plug in the -2 everywhere that there was an X in this polynomial function. Okay, you can do part of it by hand, put the whole thing in your calculator. If If you want to just get your calculator to help you with this, this would be -8, though I'm going to do part of it by hand. So this will be 4 times 3 is 12. Any negative squared is going to be positive. So that's +4 times 3 is 12. Opposite of -2 is +2. And then there's a -3. And then you can put all of that in your calculator if you want to. Or continue to do it by hand. -8 plus 12 plus 2 minus 3. And you get 3. Okay, remember, f of anything, f of x, f of a number, f of anything, that is y. So I now have like an extra point to plot, which gives me nice, specific height. In other words, it gives me what's called a local max. Right in this local vicinity, I know that at -3, the graph climbs to a height, right at -2, excuse me, right at -2, the graph climbs to a height of 3. And all I'm doing is plotting that point. So instead of just guessing how high it goes, I actually am showing it. So you could see that there is a lot of knowledge in being able to graph this thing by hand, and basically no knowledge other than how to adjust a window. You're doing it by the calculator. You're here to learn the background theory, so make sure you can demonstrate it. Okay, and that is the graph. Moving on, let's look at another example here. And we're going to go through the same moves so I can repeat what I do for finding the x and the y-intercepts and all that. All right, so here we go. Okay, is the degree even or odd? Remember, it's all about whatever the highest degree is. So that highest degree is even. I'll just label it so you know what I was right there. What is the leading coefficient? The number out in front of it. What is the leading coefficient? Negative. Anytime you have an even degree with a negative leading coefficient, both ends go in the same direction because it's even, and they both go in downward, negative direction. So they're both going to go downward. So you just answered these next two questions. What does the right side do? It falls. What does the left side do? It also falls. What are the x-intercepts? You find them by letting y be equal to 0 in the function that you started with. So using this function and replacing this with 0, copying what I have on the right hand side. Okay, as I said, in order to be able to carry through with finding the x-intercepts, which you must be able to do to carry on with the graph, you have to factor. So now there are other ways to find x-intercepts, but for you guys, you're going to be going through all your factoring maneuvers right now. Notice that everything I'm finding is an integer. These are producing integer answers because that's all your XY grid has to offer. Okay, so when you try to factor this, let's see, it's fourth degree. It does have a common term. There is something that is common to all three terms, and you are always required to take that out first before deciding, hey, can I do any additional factoring? Always take the GCF out first. So let's see. Each of these has at least an x squared. You might want to take the negative out. So let's see, we could take out, they don't have any coefficients in common because this only has a 1 in front of it, but they all have at least an x squared, and I'm going to take the negative out just to make the remaining factoring a little bit easier. So I'm going to take out a negative. I'm going to take out an x squared. That'll be my GCF. You always put one parenthesis next to the GCF and use it as a multiplier to regain each of these terms. So negative x squared times what gives you x to the fourth? X squared. Negative x squared times what gives you this? Well, that would be, let's see, I want to end up with a positive 4, so negative times negative would be that positive 4. X squared out here times an additional x would give me that x cubed. And then negative x squared times what gives me this negative 4x squared. That would be positive 4. Okay. Now I see that even though I've taken out this GCF as a taken out this common factor, I still have something that I can factor. So this may be called guess and check depending on what method you use to factor it, but you can factor this further. So this is a negative x squared, and then I can break this down by breaking up the first term into two factors. That would be x times x, and breaking up that back term into two factors. And remember, there's two different ways to factor this. You can factor this as 1 times 4. You can factor it as 2 times 2. The factors that you choose have to add up to this number. The only way you're going to get that to happen is the 2 and the 2, because 1 plus 4 is not negative 4. You can't get a negative 4. You get some sort of 5. So we're going to use the 2 and the 2, and both of them have to be negative. You should be able to multiply these to get the back number, but add them to get the middle. So now we have this all factored, but you're going to want to put this in power form, because remember, these powers determine the multiplicity. You have a binomial factor being multiplied by itself yet again. So that means it is this binomial factor squared. Remember, these powers tell you the multiplicity. Now, they're also going to, remember, all of this is equal to 0. They're also going to give you the zeros. But again, this is the multiplicity that's going to tell us what to do at the zeros. Okay, what are the zeros? Or in other words, the x-intercepts. I'll continue that right here. Remember, x-intercepts are where the graph hits the x-axis. They are also called zeros, and that's because by setting that equal to 0, or because the y value is 0 at that point. So let's see. We have two different kinds of factors. We have one that's called negative x squared that we can set equal to 0 and get some answers off of that. And we have this one called x minus 2 squared that we can get some answers off of. Okay, so I mean, it's up to you. I mean, you could just solve this by observation. What could you possibly square with a negative in front of it to get 0? The only answer that can possibly be is 0. Or you can go through steps. You could say divide by -1, divide by -1. At that point, you would have x squared equal to 0. You could take the square root, take the square root, you'd still get the same answer. So this is one of your x-intercepts. Remember, this came from over here. The multiplicity was even. Okay, you had an even multiplicity for the factor that produced this 0. And when the multiplicity is even, that means you are just going, when you do approach that x-intercept in the graph, you are simply going to touch it, not go through it as we did in the last problem. You're going to graze that x-intercept. In other words, bounce right off of it. Okay, when you go to give this answer, you might want to think of this as the square root property, excuse me. So take the square root here, take the square root here. This will knock the square off here, leaving you with just x minus 2. Square root of 0 is 0. Bring the -2 over here. You have x equal to 2. So here's your other x-intercept. Again, this came from this factor. It had an even multiplicity. So therefore, when you do plot this point and you approach it on your polynomial graph, you will only touch it, not go through it. Let's actually get a visual on what that means. So let's take our information. We're going to bring it to the graph. Don't forget, you also have a y-intercept, which is why I'm dragging you through all these steps so you don't forget to find any of the pieces that are pertinent to the graph. Y-intercept is found just by letting x equal to 0, allowing x to be equal to 0. So let's go ahead and find that. So our function was f of x, and you can, it's up to you how you write it. It is going to be equal to y. But you're letting the x value, just as it says right here, you're letting that be equal to 0. Our function was negative x to the 4th, so that term's gone, plus 4 times x cubed minus 4x squared. So it turns out that this is 0 plus 0 plus 0. So f of anything really stands for y. Your y value is 0. Or your y-intercept is 0 because you let x be equal to 0. So now bringing all of this to the graph, let's put everything we have. We have a y-intercept of 0. We have an x-intercept of 0. When your x-intercept is 0 and your y-intercept is 0, that just means it's the origin for both of them. So that serves as an x-intercept because it's on the x-axis, and it also serves as a y-intercept, the origin. All right, so we've put both of those things on the graph. I put this on the graph, I put this on the graph. I have not put the 2. At x equal to 2, we have a point, so 1, 2. Once you have everything on the x-axis, let's go put those the end behavior in there. We said that on both sides, on both the right side and the left side, we're going to fall. So we're going to fall, and when you're going down, you want to put it underneath. And you can make the line straight if you want. Now you also have to figure out, what am I going to do as I go to approach these points? Remember, we talked about multiplicity. That means as you approach these two x-intercepts, you are only going to touch them. You're not going to go right through the x-axis. You're going to touch it and bounce off of it. But if you're going to touch this and bounce off of it, that means all of a sudden you're going to be going down. Well, how far down do you go? So we did put the x-intercepts in there. We even put the y-intercepts in there. You should put all those intercepts in there. We talked about the multiplicity. We put the ends in there. Remember, this is a specific order of steps that you're doing the process. I mean, it really doesn't matter whether you put the x-intercepts or the y-intercepts first, but get it all before you start graphing. But when you go to start approaching these x-intercepts, you also have to consider that multiplicity. You have to know how to approach the x-intercepts. Should you go right through them, or should you? In this one, we are just touching them. That's what I'm referring to as bouncing. So now all of a sudden I'm going down. I want to know how far to go down. I see that between these two x-intercepts there is positive 1. So I'm going to see what's going on at positive 1. Okay, so right now I want to know what happens when I plug in 1 into this function. The function again went negative x, and I'm plugging in a positive 1. So the negative was out here, and then it was x to the 4th plus 4x cubed minus 4x squared. Okay, so 1 to any power is a 1, so this is easy to do by hand. So we got 1 with a negative out in front of it. We got 1 again, this 1 cubed, but times 4, so that's a 4. And then this is 1 squared, that's 1 times negative 4. So these 4's take each other out, you end up with negative 1. So when you plug in positive 1 for x, you get this value for y. So you're just plotting a point. So at 1, go to negative 1. So I now know how far to go, which I was almost about to go too far. At 1, go to negative 1. So we're going to go down that far. Remember, we got to hit this point right here. So we went down, we're going back up. We're only going to touch it, and that's because this had even multiplicity, so did that. So when I approach this point, I just touched it and bounced off of it. Here I'm touching it and bouncing off it again, connecting to that right end right there, and completing my graph. And that's what your graph looks like. And you can verify these, and you're going to have to produce all the steps by hand. I sound like a broken record. Okay, so that's it. Now let's move to the next one. How many more of these we have? Okay, so in this next example, you have a negative leading coefficient, maybe a little bit harder to tell what the degree is, but as we practiced in previous problems, all you have to do is not really multiply this whole thing out in order to tell what the leading degree, what the leading coefficient and the highest degree is, but just consider that this square would make that term, if you were going to do a little bit of multiplication, it would deliver a square to that term. The leading coefficient would be that -2, and then here you'd have an x to the first degree. So altogether, that would be x cubed, because when multiplying, you add the powers with that leading coefficient. And this one term is going to help us determine what the ends are doing. We know that it's third degree, so it is the degree of the polynomial odd or even? It is odd. What's the leading coefficient? -2. When you have an odd degree and a negative leading coefficient, that determines the end behavior. Anything that's odd, you're going to have one side go up, one side go down. But specifically, when it's an odd degree and a negative coefficient, instead of the right going up and the left going down, it's the opposite of that. The left goes up and the right goes down, but they definitely go in opposite directions when the degree is odd. Maybe you can remember O for odd, O for opposite directions on those ends. Okay, that negative meant that instead of this going up and this one going down, reverse it. Okay, so what does the right side do? This is the right side, it falls. What does the left side do? This is the left side, it goes up. It rises. We use the word fall and rise. Okay, find the x-intercepts. Again, we have practiced that in several problems so far. Let f of x be equal to 0. Replace the y with a 0. So up in this function right here, I'm going to put a 0. Good thing about this one is that it's already in factored form, so that makes it good. And then you have x plus 2. So when it's in factored form, you get out of doing that work and you can go right into the x-intercepts. So here is one of your factors right here. You just want to set the factors that contain x's, because actually this is a factor, this is a factor, this is a factor, but you only want to set the factors that have x equal to 0. So you can create these equations that'll give you your x-intercepts. Okay, so as we continue this, if you take the square root here, you'd have to take the square root here. This square root takes away the square, leaving you with x minus 1. Square root of 0 is 0. Bring this -1 over here by adding 1, and you get x is equal to 1. Remember, you have to look at the multiplicity. We got this expression right from here. Notice that the multiplicity is even. Multiplicity. Okay, the multiplicity of this particular x-intercept, because it came right from here, where the factor had an even number, that multiplicity was even. And when it's even, that means that when you approach this point, you are just going to touch it, not go through it. Okay, then we have this other factor right here, x plus 2. We can create our equation by setting it equal to 0 and solving it. So x equal to -2 is another x-intercept. That had a power on the outside of the parenthesis of 1. And 1 is a odd multiplicity. So the multiplicity was odd. as you can see right there. And when you have an odd multiplicity, you're going to go through the point rather than touching the point. Okay, so we now know what our x-intercepts are and how to approach the x-intercepts. The y-intercept. The y-intercept, you're going to let x be equal to 0. So get in that function that's up here, and everywhere you see an x, you're going to put a 0. So this is the function evaluated at 0. We had an x minus 1 in the first parenthesis with a square, and then we had an x plus 2. I'm putting zeros wherever I see an x. So we're now going to be evaluating. It's a lot easier to find a y-intercept than an x-intercept. Sometimes you have to factor for the x-intercept. So this is going to be negative 2. 0 minus 1 is just minus 1. 0 plus 2 is 2. Getting closer to that answer. This will be negative 2. This is 1. Anything squared is going to be positive. Times that 2, so this will be negative 4. So I now know that y is equal to negative 4 when x is 0. If you want to write it as a point, I allowed x to be 0 and the y coordinate turned out to be negative 4. That is your y-intercept. Okay, so now we also have the y-intercept. We have our x-intercepts. We actually know what to do at those x-intercepts. We're going to touch one of them, just graze it and bounce off of it, while the other one we're going to go through it. Okay, moving all of that to the graphing grid. Okay, so my x-intercepts are 1, and my other x-intercept is negative 2. I'm going to put my ends in there. My ends are, let's see, look at the picture up here. You might want to use these little marks. I like to do this instead of writing it like that because these tell the whole story. You're going to go down on the right, up on the left. Okay, when you're going down, you do it underneath the rightmost point. And when you're going up, you do it above the point. Okay, I'm going down on the right, up on the left. Okay, now we're going to through those points. Okay, so let's see. This x-intercept of 1. Let's go check out our work up here. The x-intercept of 1, it had an even multiplicity, so that means we're going to just touch that x-intercept, which means right away, as soon as we touch it, we're going to go down. How far down? So I'm going to touch up to know how far down to go. My y-intercept was negative 4. 1, 2, 3, 4. So right there, which is where negative 4 is, I have a point that I can head for. So I'm going to bounce off, go to that y-intercept, head for the next point, which, let me think, what am I supposed to do when I get to that point? I'm supposed to, this is negative 2. And it came with an odd multiplicity. I'm going to go right through it. That means I'm going to go right through the x-axis. That makes sense because I have to connect to this end. Notice that with these problems, there is a maximum number of turning points. So we had said that if based on the degree, we can tell what the maximum number of turning points is. The degree of this function, right back to the beginning, was third degree, degree 3. So the maximum number of, if this is n, maximum degree, then n minus 1 or 2, that is the maximum number of turns. Most times that the graph is going to turn is twice. And let's see what ours did. It turned once here and it turned another time there. So it does have 2 turning points. Let's make sure that we addressed that question in the other graphs. Let's go back to the previous graph. Make sure that we got that. Okay, so in this previous graph, let's see, what was the degree? The degree was 4. So what's the maximum number of turning points? If the degree was 4, and that represents n, then we get the maximum number of turning points by n minus 1. So that would be 3. So how many times did this actually turn? It did turn 3 times. It doesn't always turn the max, whatever the maximum number comes out to be. That's the most you're ever going to see. So there was one turning point here, one turning point here, one turning point here. And I don't know if we answered that question because once you graph it, on this one we did. No, actually, you should answer it first because the graph is not always going to reveal, as I just stated a couple seconds ago, it's not going to always reveal the maximum number of turning points. So you go based on that rule. Whatever the degree is, subtract 1, that's the maximum number of turning points. So we've done 3 graphs at this point. And let me check out these other ones. I'm going to make sure that we didn't do this already. So this is x to the 4th. Okay, so here is the next example. Just remember, when you watch these videos, any of these videos, you can just slide around to the problems that you need. I mean, a lot of you are going to need every single example in order to do well and to have enough examples to get the homework, and some of you won't need as many. So, it's to your discretion. I suggest that you watch the whole thing. I mean, typically, there's always a little bit more material than what fits into an hour and 15-minute class in order to give you a thorough presentation, but sometimes they go a little bit over. So sorry about that, but, again, you can skip around. You can slide it to the problem that you need. So here we have, on this example, x to the 4th minus 2x squared plus 1. What is the degree? This is degree, whatever the highest power is. It is even. What is the leading coefficient? 1. Even degree, your ends are going to go in the same direction. And if it's a positive leading coefficient, they are both going to go up. Okay, determine the end behavior. We just did. This little picture is the end behavior. On the right side of the graph, it rises. On the left side of the graph, it also rises. What are the X-intercepts? That's usually where most of the work comes into the problem, especially if it's not factored. This is not factored. So, and we're also, trying to practice with multiplicity and what that means. So we're going to let f of x be equal to 0. So right in there, I'm putting a 0, and I'm copying the rest of the polynomial. X to the 4th minus 2x squared plus 1. Okay, then you're going to try and factor that. Okay, there's 3 terms here, so that would be guess and check method, and it goes by other names as well. You're breaking up that front term to fill in the front position. What times what is x to the 4th? That would be x squared. What times what gives you the back term? That'll fill in these back positions. So use that front term, break it up into factors to fill in the front positions. Use the back constant to fill in these back positions. When it's positive, these are both going to have the same sign, and this is what they both are. All right, so we have it partially factored, and that's because these guys factor even further. So we can break this down into x minus 1. Again, this is difference of squares. We've already factored this once in this outline. This right here, and this is going to factor the same way, breaks down into x minus 1, x plus 1. This factors the same way, x minus 1, x plus 1. But you want to write this in a way that you're going to be able to be really clear on the multiplicity. So remember that this is the same thing as, let's see, that x minus 1 occurs to a power of 2. There it is there and there. And then the x plus 1, same thing. X plus 1 occurs to a power of 2. Okay, then once you get this completely factored, you're going to want to get the zeros of it. Don't forget, you're looking at the multiplicity right now. Whatever these x-intercepts do turn out to be, they are going to be touching points. The multiplicity of both of these is even, which means they're going to be touching points, whatever those x-intercepts are. We get the x-intercepts by taking the factor and setting it equal to 0 and solving it. So taking the square root here and the square root here, you get x minus 1 is equal to 0. And then bringing this over here, you get x equal to, right up there, x equal to 1. That's going to be one of your x-intercepts. Don't forget to take the other factor and set that equal to 0. So it'd be x plus 1 squared is equal to 0. Taking the square root of both sides, you get x plus 1 equal to 0. Bring that over there. You get another x-intercept of negative 1. And we will be touching at those 2 points because the multiplicity of each of these x-intercepts was an even power, indicating that they are touching points. Y-intercept. The y-intercept is going to be found by letting x be equal to 0. So we're going to do that now. So it's f of 0. This is really easy because it's not factored. You're plugging in x to the 4th minus 2 times x squared plus 1. So this is gone, gone, 1. So your y value is 1. You can even write it as a point if you'd like. When you let x be 0, your y coordinate is 1. So that would be your y-intercept right there. Okay, then, what is the maximum number of turning points? Well, the degree of this particular function was 4th degree, and then that represents the n in the theorem. And you just subtract 1. So maximum number of turning points, 3. That's the most number of turns you can expect to see. Going to put everything on the graph now. We have x-intercepts. Notice that I keep putting those on first. We have an x-intercept of negative 1. We have an x-intercept of positive 1. We have a y-intercept of 1. And we need to paste our ends with respect to the x-intercepts. We're going up on either side. Whoop. Move that over a little bit so that I'm right on top of that. Okay, so now we're going to go from these ends that we've pasted in place. Both ends go up, and we're going to pay attention to our multiplicity. We're going to be heading for the x-intercepts from these ends, just grazing that x-axis. So bounce right off of it, head up for that y-intercept, go and catch that other x-intercept, and up to catch the other end. And that's the graph. Okay, I believe this is, oops, I guess I said it too soon. I think I may have copied some of these pages twice, so hold on, let me make sure we didn't do this one yet. Negative 2 x minus 1 x plus 2. Yeah, that's just a copy of one we did already. We did that one already. Yeah, so that's it. That's all of them. Okay, so that concludes all of section 3.2, and I will join you again for the next video for section 3.3.